Good morning. Good morning, and thank to the chairman for the presentation. I'm Andrea Maroni from University of Strathclyde, and today I'm going to present our project on bridge Scour risk management. This is the outline of my presentation. I will start introducing the motivation, what is a Scour monitoring system, and the objective of our project. After a brief description of what is a Bayesian network, I will present you our Scour other model. Then I will describe the case study used to test our developed system, and finally I will show you the decision model developed. Flooding and scour are the leading cause of the failure of bridge worldwide. Around 1,000 bridges fail in the US in 40 years, and in the UK there were 140 bridge collapses in the last century. In Scotland now there are more than 20 bridges, both roadway and railway bridges, considered at high scour risk. Scour is the erosion of the bed material due to water flowing. There are two types of scour. The constriction scour, because of the presence of the bridge brings to a channel with reduction that leading in an increase in water velocity. And when this water velocity reaches the critical value, the bed erosion starts. The second type of scour is the local scour that is due to vortices at PIERS base. And of course, the total scour depth is simply the sum of these two components. Probe to measure scour exist on the market. In our project, we employ this sensing technology developed at our university, and it consists of a sensing rod equipped with electromagnetic sensor able to detect change in permittivity in the surrounding soil. So the sensor allows to separate compacted soil, water, and redeposited soil. This probe is installed at the A76200 bridge at New Cumnock in Scotland. That bridge is a 3-span Manchuri arch bridge with 2 piers in the riverbed and founded on spread footing, and it has experienced significant scour in the past. So in principle, we have the technology to monitoring the scour at every pier of a bridge network, but monitoring an entire infrastructure network is not economically feasible. It can be overcome by monitoring only limited and critical location and by using a probabilistic approach. So the idea is to monitor only critical piers, and with the scour monitor at that piers, the probabilistic tool, in our case the Bayesian network, can estimate the scour depth at unmonitored bridges. So our aim is therefore to develop a decision support system consisting of a scour radar model that can estimate the scour depth using information from monitoring of scour depth itself, and a decision model that can inform decision about the scour management. But before starting, what is a Bayesian network? A Bayesian network is a probabilistic graphical model where the random variables are represented by the node, and each arrow represents their conditional dependencies. For example, in that case, x1 is independent and influences x2, and x1 is the parent node of x2, and x2 is the child node of x1. There are two ways to make Bayesian inference in the Bayesian network. The first one is the prediction analysis, where we can predict the child node distribution starting from an evidence on one of its parent node. And the second one is the updating analysis, also called Bayesian learning, where we can update the parent node distribution starting from an observation of its child node. Our system was developed following the model provided by the procedure BD9712. It's a procedure used by transport scatter to estimate the scour starting from the water flow. So the water flow is the starting variable of our Bayesian network. The Manning equation was employed to describe the relationship between the water flow and the water level, and a model error is employed into the model itself. These correlated model error are the most important node into the Bayesian network because they allow to correlate different bridges, even they are not nothing in common, into our Bayesian network. The next step is the calculation of the average value of the constriction scour, and a nonlinear system of 3 equations in 3 variables is employed in the Bayesian network. Those 3 equations are the Colebrook-White equation, the conservation of mass, and the Bernoulli equation. And a correlated model error is added again to the Bayesian net, to the model. The BD9712 provides this table to pass from the average value of the constriction scour to the scour depth at along the channel, every position along the channel width. We model these factors through 2 errors, one constant and one that depends on the position. The local scour depends on the channel width, the pier width, corrected by some factor, including its shape, its alignment to the flow, and the local water depth. And a model error is added as well also to the local scour model. And finally, the total scour is simply the sum of the 2 components. So this is the final Bayesian network that allow us to estimate the total scour at the pier starting from the water flow. The Bayesian network can be extended to a bridge with n pier into the riverbed because we can find correlation in the average value of the constriction scour and the water level because they are in common for every pier. And also the Bayesian network can be extended to a second bridge with n pier as well, and in that case the correlation is in the model error, as I said before, because the model used to estimate the scour at both bridges are the same, so same model, same error. Observation from monitoring system are used so to update parent nodes in order to have a better estimation of the child node of unmonitored bridge. In our case, the observational quantities are the total scour at 1 pier thanks to the scour probe, while data about the water level are provided by an environmental agency. So we built this case study consisting of 3 bridges in southwest Scotland in order to demonstrate the functioning of our Bayesian network. And the idea is to monitoring just 1 pier at the first bridge in order to estimate the scour level at all every location of the unmonitored bridges. So the 3 bridges are all over the same river, and we assume correlation in the riverbed sediment. The first bridge is the one I've already showed you, and is the one where 1 pier is instrumented with the sensor probe. The second bridge, the Guildhall Bridge, is again a 3-span stone Manshury arch bridge with 1 pier in the riverbed founded on spread footing, while the third bridge, the Dascombe Bridge, is a completely different type of bridges. It's a steel concrete composite bridge with 7 span and 1 pier in the riverbed. So this is our Bayesian network for our case study, where we can see the 3 different bridges and the model error that correlated all of them. If we don't have any observation into the network, we can predict the local scour, the total scour at every pier starting from the prior distribution of the parent nodes. As I said before, the observational quantity in our case are the total scour at the first pier of the first bridge and the water level upstream each bridges. So when these observations enter into the Bayesian network, we can update the parent nodes in order to have a better estimation of the scour at unmonitored bridges. We adopt a log normal prior PDF for the river flow and a normal PDF defined by zero mean and a coefficient of variation for each model uncertainty. These are the results a priori, so using a prediction analysis, and that means that there's no observation now into the Bayesian network. We used a Monte Carlo simulation to get this result, and as you can see, we got a very wide distribution with a standard deviation of around 80 centimeters. That is completely unsatisfactory. So let's now introduce the measure of the scour at the first pier of the first bridge. Let's assume that the sensor measured 45 centimeters of total scour, and it is intuitive that the algorithm and the observation can improve the accuracy of the estimation, because the algorithm estimates a value of scour at the second pier of the first bridge that is equal to the one measured, and that value is the most probable value because the two piers belong to the same bridge and the water flow is the same. But since it is an estimation, we have an uncertainty equal to 17 centimeters, which is anyway better than the prior results. So in that case, we got an accuracy, an increase in the accuracy of around 80%. The algorithm also estimates with good accuracy the total scour at the unmonitored bridge with a standard deviation close to 21 centimeters, and again, the increase is in the order of 80%. Yeah. Transport Scotland classified their bridge to scour risk with this graph according to the relative scour depth, that is the total scour divided by the foundation depth, and a priority factor. They also follow a visual decision scheme, whether closing the bridge or not, according to water level threshold alone. So they fix this threshold by implicitly choosing a level of risk they are willing to accept. So our idea is to add information of scour to their decision framework. So the estimation coming from the Bayesian network and data from our scour monitoring system are used to inform decision in our proposed decision model. We express the scour failure probability as the probability that the scour demand is greater than the scour capacity. We model the scour capacity through a scour fragility function that reflects the scour risk classes from Transport Scotland, and the scour demand as a normal distribution centered into the Transport Scotland threshold. In that way, the prior scour failure probability is the probability implicitly chosen by Transport Scotland when they fix their threshold. The Bayesian network provides an updated scour estimation, so express also a posterior scour demand with a smaller standard deviation and centered to a new threshold. But to be consistent with the threshold chosen by Transport Scotland, the scour probability of failure must be stay equal to the one calculated a priori. So the new threshold is the value that satisfies that equation. So let's assume that the priority factor is equal to 2. So according to that graph, the prior threshold for Transport Scotland is equal to 2.3 because it's the value defining the boundary between class 2 and class 3. On the right, we have the plot of the two scour probability of failure. The prior probability of failure in red is constant because the value of the threshold was chosen a priori by Transport Scotland. So the intersection between these two lines give us the new threshold that satisfy that equation. So starting from a prior threshold of 2.3, the updated observation from the Bayesian network allow us to increase this threshold up to 2.67. By concluding, we proposed a decision model, a decision support system consisting of a scour ADAR model that is able to estimate the scour depth starting from scour monitoring data, and a decision model that can update the scour threshold after which the bridges are closed. We built a case study of 3 bridges in southwest Scotland in order to test it, And we found that the probabilistic framework demonstrate that data from observation from Scour monitoring system increase the accuracy at unmonitored bridges by the 80%, and also, moreover, the outcomes from the decision model present an increase in the Scour threshold from 2.3 up to 2.65 that could help the agency in reducing unnecessary bridge closures. These are the reference for the presentation, and thank you for the attention.
Questions?